Hello friends, Mr. Burrell here. We're in Unit 10, kind of talking about some introductions to trigonometry. We've talked a lot about angles. We've talked about angles in degrees, angles in radians. We've talked about drawing angles. We've talked about coterminal angles. We've talked about identifying reference angles. Lots of things to do with angles, and those things are going to prepare us, along with what we're going to talk about in the next couple of sections, majorly for the next couple of units of trigonometry that we discuss. So now these last couple lessons that we talk about in this unit are going to be reflecting on right triangle trigonometry. So sine, cosine, and tangent, that kind of stuff, the SOHCAHTOA stuff, using the Pythagorean theorem. Those kinds of things that you learned already in Math 2, we're going to review a little bit. Again, because it's been a little while, we're going to review because we're going to be using that for the upcoming units. So before we get into reviewing right triangle trigonometry, we're going to go over some special right triangles. There's some specific relationships that we know about, some very specific right triangles that are going to come in handy when we start talking about relating our right triangle trigonometry to the angle measurement type stuff that we've just discussed. So, by the end of this lesson, this is what I hope you're able to do. Know the pattern of a 45-45-90 triangle and can use it to solve for a side length, and know the pattern of a 30-60-90 triangle and can use it to solve for a side length. I'll talk about what that means, what those special triangles are here in this lesson. But we're going to talk about the patterns that exist between these special types of right triangles. So, do you remember what an isosceles triangle is? An isosceles triangle is a triangle where two of the sides are congruent and then correspondingly two of the angles are congruent. That's an isosceles triangle. Also, this would be an isosceles triangle because these two sides are congruent and these two angles are congruent. Any triangle where two of the sides are congruent and therefore two of the angles are congruent, that's an isosceles triangle. So this, I've kind of like flipped it on its side and then written it up right over here. This is an isosceles right triangle, meaning that these sides are congruent and also this angle up here is 90 degrees. Well, if this angle is 90 degrees and all the angles on the inside of a triangle have to add up to 180, then each of these angles must be 45 degrees. Because 45 plus 45 plus 90 equals 180. So this is what we call a, like I said on the objectives slide, this is a 45-45-90 triangle. Or an isosceles right triangle. That's another way you can think about it. And this has some special properties. First of all, we're going to do a little discovery here. We're going to figure out what this side of the triangle over here would be, even if I don't know the lengths of these sides. So, I know that these two sides are the same. Those two sides are congruent because this is an isosceles triangle. Well, what does the Pythagorean theorem say? It says a squared plus b squared equals c squared. You're pretty familiar with that. I hope you've been exposed to it before. Where a and b are the legs of this triangle, and c is the hypotenuse. This is c right here. Well, since the legs of this triangle are the same, I could write a squared plus a squared equals c squared. Well, let's find out what c is in terms of these other two sides. Well, a squared plus a squared, that's 2a squareds. 2a squared equals c squared. So if I wanted to find what c was, I would square root both sides. I'd get c equals the square root of 2 times, well, the square root of a squared is just a. So I'm going to write that as a times the square root of 2. So this side right here is a times the square root of 2. There's the math that I just did. So basically, no matter what a is, if I know the length of this side over here, any of these sides, the length of the hypotenuse is going to be the length of this side multiplied by the square root of 2. every time. It doesn't even matter what A is. The length of the hypotenuse will be that side multiplied by the square root of 2. Ah, that's crazy. I think that is mind-blowing. Let's look at a couple of examples. First of all, I think this is the picture that's in your guided notes if you're using the guided notes. This is a 45, 45, 90 triangle. I used A as an example, so this would be A, this would be A, and this side over here would be A times the square root of 2. The picture you have uses N and N times the square root of 2. Same principle. If I know the lengths of the sides of this 45, 45, 90 triangle, I can find the length of the hypotenuse without even having to do anything, because that relationship will exist every time. So, I have this isosceles right triangle. This side is the 6, this side is 6. What's this side going to be? Well, it's going to be 6 times the square root of 2. Don't believe me? 6 squared plus 6 squared is 72. The square root of 72 is 8.485. Well, 6 times the square root of 2 is 8.485. Ah, that's so cool. That relationship will exist every single time. So the length of that side is 6 times the square root of 2. What if I had the square root of 2 and the square root of 2? Well, the length of this side would be the square root of 2 times the square root of 2. Or in other words, the square root of 2 times the square root of 2 is the square root of 4, or 2. So the length of this side of the triangle will be 2. Because it's these sides multiplied by the square root of 2. Ha! Crazy. So cool. Okay, let's practice. This would be an example of some problems you might see on the homework. So I have a 45, 45, 90 triangle. I know that because I was given that this angle was 45 degrees and this angle was 90 degrees. And I know that this side here is 6. That's the only side that I'm given. Well, I know that in a 45, 45, 90 triangle that the two legs have to be the same, so I know y is going to be equal to 6. And I know that the hypotenuse always will be one of the legs, or 6, multiplied by the square root of 2. So this side is 6, this side is 6, this side is 6 times the square root of 2. And you can leave it like that. You don't need to reduce that to a decimal if you don't want to. You can leave it as in radical form. Okay, on this problem, I have another 45, 45, 90 triangle. I know because I have this right angle, and I know this angle is 45, so this angle will be 45 degrees. I'm given the hypotenuse as 7 times the square root of 2. So if you remember our little 45, 45, 90 triangle, if I had A, and A times the square root of 2, so if I'm given the hypotenuse being 7 times the square root of 2, that means each of these sides must be 7. Because conversely, 7 times the square root of 2 would give me 7 times the square root of 2. So though that is the special relationship that we're talking about with 45, 45, 90 triangles, that relationship will happen every single time. Pretty cool, I think. All right, now we're going to talk about another special kind of triangle. So do you remember what an equilateral triangle is? An equilateral triangle is where all of the sides of a triangle are the same, and all of the angles are the same. So since all the angles on the inside of a triangle need to add up to 180 degrees, each of these angles has to be 60 degrees, because 60 plus 60 plus 60 is 180 degrees. So that's an equilateral triangle. What I'm going to do is I'm going to cut that equilateral triangle in half. So I cut this right down the middle. So this angle over here is still 60 degrees. This angle now is 90 degrees. This angle up here was cut in half, so it's 30 degrees. So I have now a 30, 60, 90 triangle. Maybe some special relationships exist with this 30, 60, 90 triangle. Let's see. So we mentioned in the equilateral triangle that all these sides, sorry for the terribleness of my drawing, all three of those sides are the same length. So that means that this little half side, since I split this triangle in half, this side is going to be half the length of this side. Or this side is going to be double the length of this side. So I have this written as x and 2x. So the hypotenuse of this 30, 60, 90 triangle will always be twice the length of this short side of the right triangle. See that? Okay, now we're going to solve for this other side and solve it in terms of x. So I'm going to use the Pythagorean theorem again. This side squared plus this side squared equals this side squared. So a squared plus x squared equals 2x squared, which is a squared plus x squared equals 4x squared. Well, if I'm trying to solve for a, I'm going to get everything else on the other side. So I'm going to subtract an x squared on both sides and get a squared equals 3x squared. To get a by itself, I'm going to square root. I'm going to be left with a equals the square root of x squared. That can come out as an x, and I'm left with the square root of 3. So this side right here is x times the square root of 3. And here's all the work that I just did. So it's not incredibly important for you to remember how we figured this out. But I mean, look at that. I think that's so cool. Look at that relationship. No matter what the lengths of these sides of the triangle are, this side, the hypotenuse, will always be double this shortest side. And then this side, this other leg, this long leg, will be this shortest side multiplied by the square root of 3. Every single time, no matter what these numbers are, this relationship will always exist. That's crazy. That's cool. Let's see it in action. I think this picture right here is the one you have in your guided notes. And it's kind of helpful for me to look at this. I have my 60-degree angle, my 30-degree angle. The shorter leg is going to be x. The hypotenuse is double that. And then the long leg, this other long side over here. Oh, whoops, let me go back. This long side over here is the shorter side multiplied by the square root of 3. Short side, hypotenuse, long side. That relationship will always exist. Okay, let's look at an example. I have the short side, the long side, and the hypotenuse side. The hypotenuse side is double the short side. So if the short side is 5, the hypotenuse is going to be 10. And then the longer side is the short side multiplied by the square root of 3. So the hypotenuse here is 10. The long side is 5 times the square root of 3. Because in a 30, 60, 90 triangle, the hypotenuse will be double the short side. The long side will be the short side multiplied by the square root of 3 every single time. So then if the hypotenuse is 2, that's going to be double the short side. So this short side is going to be 1. Short side is going to be 1. And then this longest side is going to be 1 times the square root of 3, or just the square root of 3. 1, 2, and the square root of 3. What if this long side down here was 12 times the square root of 3? Well, that means this side would be 12. Do I have that up there already? Yep, this side would be 12 because it has to be this longest side has to be the shortest side multiplied by the square root of 3. And this hypotenuse is going to be double 12, or 24. That relationship will exist every single time. Okay, let's practice this one. Right here I have the hypotenuse is 10. The hypotenuse is 10 units long. So thinking back to the relationships I know about this 30, 60, 90 triangle, this short side right here is going to be half of that, or 5. Right? That short side is going to be half the length of the hypotenuse. And then this long side is going to be that short side multiplied by the square root of 3. Multiplied by the square root of 3. So without even doing any math, any trigonometry, I know those relationships, so I can fill in the lengths of those sides because of these special relationships that exist with these special right triangles. Okay, so here I have this triangle. This one's going to be a little bit trickier. You'll see something like this sometimes. So I have this long side, that's 5, and the short side multiplied by the square root of 3 should give me the long side. So to get from the long side to the short side, I'm going to divide by the square root of 3. So this side right here it's going to be 5 divided by the square root of 3. Because if I wanted to go from the short side to the long side, I'd have to multiply by the square root of 3. Square root of 3's would cancel out, and I'd be left with 5. So the short side is 5 divided by the square root of 3. That means the hypotenuse side has to be double that, or multiplied by 2. When I multiply that by 2, I'll get 10 over the square root of 3. And that would be my answer if you wrote those as decimals or left them in radical form, or if you changed it so the radical wasn't in the denominator. If you don't like that, that's fine. But I would take this right here. Those are the lengths of those different sides because of these relationships that always exist with 30, 60, 90 triangles. Here's a couple problems from your homework. So if I have this, this is a 45, 45, 90 triangle, because I have 45, 45, and 90. So if this side right here is 6 times the square root of 2, if you remember our 45, 45, 90 rules, I have a, and a times the square root of 2. So if this is 6 times the square root of 2, this is going to be equal to 6. This is going to be equal to 6. So I have 6 and 6. See, I didn't have to do any math at all in order to be able to do that. I just remembered back to what I know about the relationship between the sides of this 45, 45, 90 triangle. I know these sides are going to be the same, and that this side is going to be these sides multiplied by the square root of 2. Now, here I have a 30, 60, 90 triangle. So what do I know about a 30, 60, 90 triangle? Well, I know that the hypotenuse is going to be double the short leg, like this, and that this long leg is going to be the short leg multiplied by the square root of 3. Well, this is the hypotenuse because it's directly across from the right angle, so this short leg has to be half of that, or 4. So this side is 4, that means this long side has to be 4 times by the square root of 3. And those are those individual sides. And that's it. That's all we're doing in this lesson. I hope by the end of this lesson that you're now able to recognize and use the patterns associated with the 45, 45, 90 triangle and a 30, 60, 90 triangle, and use those patterns to solve for the different side lengths. We're going to be using a lot having to do with these triangles in the upcoming units, so it's going to be really helpful to be able to remember and recognize these relationships. There's not a required homework assignment for this lesson. The homework assignment that I have posted is extra credit, so I still encourage you, do it. Do that assignment. There's not a quiz associated with the assignment, but do the assignment because it's going to be extremely helpful for your grade, first of all, because it's extra credit, and in the upcoming units. So I hope that was helpful, and I hope that you enjoyed it as much as I did.